Okay. Okay. Thank you, everyone. Thank you for attending my defense. And my name is Xiangbin Chen. And my project is direct numerical simulation of nucleate boiling. And this work is under the supervision of Professor Stéphane Popinet and also Daniel Fuster. And so you know, nucleate boiling is very critical and important, observed both in everyday life. So in the left, I give the figure, which is a cooking case. And if you know the process of boiling, you can enable to get delicious food. And also, nucleate boiling is critical in industrial application, especially in the power plant. Yeah, it's very critical to generating the electricity. Is boiling. There are many types of boiling. These curves illustrate the relationship between the heat transfer, superheat, and the heat flux, which divide into several types. And today we are focusing on BD stage, which is the nucleate boiling stage. Here in the left eye, which is the basic experiment of nucleate boiling. And is boiling easy or fully understand? It is obvious no, for me at least. Especially in the numerical simulation, the most challenging thing is nucleate boiling is a multi-scale problem. And at least there are three regions of this problem. So the first problem is overall scale, which means the overall size of the boiling is millimeter. And then the second region is micro layer region, which you have this the micro layer is the liquid layer between the huge bubble and the solid, and the length of the micro layer is ranging from tens of microns to hundreds of microns, and the thickness of the microns is under 10 microns. So you see that the whole region of micro layer is from 1 to millimeter. And for the nano region, it's mainly talking about the contact line region. So currently, among the excellent previous works, there are three main approaches to modeling the boiling. The first one is an overall boiling with submodels of micro layer, and then the second method is that we have higher enough resolution for solving the micro layer, but without nano region model, and these have been also developed by several authors. And finally, the resolving micro layer and with nano region models. Sebastiani and Yostato also have done related work. But today, in our study, we will adopt a mesh size small enough to resolve the micro layer, but without a nano region. The reason is that the contribution of the nano region to the overall bubble growth can be neglected, suggest. So next, the problems we want to try to answer is first how to model the boiling problem, and along with the micro layer formation, and also then we want to investigate the contact angle effect in the boiling phenomenon, and also next the relationship between the overall boiling and the micro layer, and next we want to find the impact of the interface heat transfer resistance, and finally we will have a try on the boiling bubble behavior on rough surfaces. So first, how to model nucleate boiling in micro layer resolved region. This is unknown control equations, and the difference lies in the presence of the micro layer, the Soston due to phase change. So here you can see a Soston, and then the jumper conditions, which is the velocity jumper condition and the pressure jumper condition, and also the energy balance equation. So we want to try to solve this equation and then analyze the boiling phenomenon. Next, what models might to be needed when we modeling the nucleate boiling? So here I give the final result of my work. So you can see that this like these grooves is the structure, under the line is the solid, above is the initially is the liquid, and then this bubble is the water vapor bubble. So in this model, we apparently we need the Navier-Stokes equation solver, which here we use in Basilisk, and we also need to implement the energy equation in Basilisk, and then because it's a phase change problem, phase change model is also required, and besides we found some small problems, and we enhanced the solid modeling with specific boundary condition in Basilisk, and we finally we also developed a improved advection method for volume conservation and refine the contact line motion behavior. The entire code is developed on Basilisk, and the Basilisk is open source CFD code in our lab, designed for simulating multi-phase flows and other fluid dynamic problems. Most of the code has been developed by Stéphane Popinet at Sorbonne University. And the main feature, I think, of this Basilisk software is its adaptive mesh refinement feature, and also the sharpening interface model modeled by VF, a geometrical interface capture method. And next, the phase change model we add. And our phase model is actually based on the earlier work of Malan, and also extended by Yohei Sato. The key is to satisfy the boundary condition at the liquid vapor interface. So this is 7 to 9, the boundary condition. This one is the energy balance method equation, and 8 is the temperature continuity equation, and this is 9 is velocity jumper condition. And to fulfill this, the main step is actually calculate the divergence free velocity, which is this UL, because we think that the interface is advective this divergence free velocity UL, and then based on this UL, we use this UL to advect the interface while considering the phase change contribution. Then we how to get the extended UL to gas region, which is how to get the UL divergence UL, which is first we solve the pressure potential equation, and then this is known, and we update U from the pressure term, and then we know that the feature of this divergence of the velocity equals to a source term, and we add an additional pressure Poisson equation PS, which is this one. The right term of the Poisson equation is opposite to the previous one. Then you update the additional US from the PS, and you will find that the divergence of this is opposite to the previous one. And if you add U to US, then you will get UL. And if you get the divergence of the UL, you will find that it is 0. So here following is the red region in the we had the additional Poisson equation solved, and the arrow line place it the velocity where the velocity updated. And next is to how to advect the interface using ER. And this is direct. That is, we need to update the following fraction rate by color function, which is this one. And this 13 equation is divided into 14 and 15. For the 14, the right is 0, so we can use in the classical advection following conservative scheme, which shows ABC, which you initially have this interface, and then you calculate the flux from the right, from the left, also from the right, and then you updated the foreign fraction interface. And for the 15, it's actually updated from due to the foreign change, due to the phase change, which is you calculate the mass transfer rate, and then you transfer into a distance, and then you can calculate the volume changed, and then you added this volume to the C foreign fraction in C. And next is how to model the embedded solid. Actually, in Basilisk, Stéphane Popinet has already fulfilled in Basilisk implemented the embedded solid model, which is the key. The basic is to calculate. So, for example, this one, this is solid, and this is liquid. Oh, and then you need to calculate the flux of this partial phases, and the basic of the get the flux is to interpret the flux of the red point from the black point in the left figure, and also the same methodology for the point at the solid surface. We interpret from the red black point in the flow region to the value at the surface. And next, we need to add the temperature equation to the solver. So the equation we need to solve is 18, and the boundary condition applied using, we also using the embedded mass solid methodology. For example, if you want to apply the conjugated solid boundary condition 19 at the solid water interface, you actually get a relationship between the liquid temperature at the blue region and the solid region using this boundary condition, and then you get the relationship of this hollow triangle and the hollow circles, and then you can solve this equation of the equation with the specific boundary condition. So next, we found some small, not small, but behavior that is not too good. So the first we found is that we developed a volume conserving improved method for embedded solid models, which is, so what is the issue in the original code is that not an issue, but volume fidelity is not well conservative when solving color functions with embedded solid method. So the volume is not conservative when used the embedded solid model, and the reason is that we make the wrong foreign fraction conservative. What I mean is that first I introduce the foreign fraction. We have three foreign fraction, which is C is the foreign fraction, the normal foreign fraction that the original method want to make conservative, and the CS is the foreign fraction of the solid. And another, I call it true foreign fraction, is actually the foreign fraction of the true liquid, which is in the right. And if we, in the scenario of embedded solid, so in the left is the case we want to implement, and which is gas, and blue is the liquid, and brown is the solid. And if we the C foreign fraction is actually the blue region here in the middle. So you see there is some form fraction of the liquid inside of the solid, but the original method tries to keep this form fraction conservative. Well, we think that the form fraction need to be conservative with the C-tilde form fraction, which is the blue region in the right figure. So after knowing the reason that the solution is very direct, solve the color function for C-tilde, which is the form fraction of a true form fraction, and the equation solved is the same as the form fraction, the original form fraction, which should be noticed that when you calculate the flux across the faces, you should truly calculate the form fraction of the liquid. And the details procedures, I will have a quick look. So you have this form fraction, and here 21 to 25 is the procedure that in Basilisk to advect the form fraction C, and we for C-tilde you follow the same procedures, but the test should be taken when you calculate the advect volume C, which is here. So after updating C and the C-tilde, we actually recalculate the C from C-tilde based on the interface equation, and also the relationship between the volume and the alpha. But it's for us, we just adopt a more direct method, which is by numerical method, the bisection method. And to validate the method, we actually use a Cecil drop on a flat plate, which is here in the top figure, left figure, we have a solid, and on top of the solid we have a drop, which is a circle, hemicircle, and hemispherical shape. And initially the contact angle of this drop is 90 degrees, and because we set a different static contact angle for the case, so the drop will relax to its static condition. And for this situation, we have some result. And here in the bottom, I also show want to adjust the concept of the form fraction C and the form fraction C-tilde. And then this is the result. We will focusing on the right figure in the top, which is relative volume error versus time. And the original method, the result of the original method is deficit using the dashed line. So, and the blue dashed line at the bottom is actually the relative volume error of the C field, and you see that this value is almost 0. So we know that the original method tries to keep the form fraction of C to a conservative, but the behavior of the C-tilde in the original method, which is the red dash line, is not ideal. And in our method, which is the solid line, let's see the red solid line at the bottom, which is corresponding to relative volume error of the C-tilde, and we see that this relative error is low. So let's get started again. There are two reasons for this small contact angle. So one is that we couldn't get the exact position of this triple point, and the solution is to directly calculate the position of the red point here using the equation of the interface of the liquid and the solid surface. And the second is that the form fraction is not precise in the ghost fluid region. which is in process of the liquid form fraction. So here is the original one that we didn't calculate the form fraction at the mixed cell, and we think that the correct one is to calculate this one. And then when we calculate the height function, then this position can be properly calculated, and then the curvature would be better. But the reason that we in the original method that doesn't calculate the form fraction of this position is that if we calculate this one, then and we add the form fraction to the liquid field, then the total form fraction will be changed. That means the mass conservative will not be conservative. So so for this reason we will only use this form fraction to calculate the height function. And the test cases we give is the cell drop on an inclined plate. The left is my result and the right is the standard case in Basilisk. We could see a nice a bad result at a small angle. Here the smallest is 5 degrees, and here the smallest angle is 15. We see the discrepancy. And so I will quickly go through the algorithm in Basilisk. First, we calculate the source term from the temperature region, and then we advect the form fraction and the temperature using the divergence-free velocity, and then we advect the interface due to phase change. Then we solve the temperature equation at the three regions. Then we solve the momentum equation 5 to 6, surface tension, advection and viscosity, and finally we're solving two Poisson equations. One is the normal, another is used to get the divergence-free velocity. And then follows the test cases. So again, the cell drop, but this time is on top of a circle, and the following give the relative error versus time at the different contact angles, and the behavior is not well only when the contact angle is 165, and otherwise it is good. And this study is the mesh convergence study. We changed the mesh size and statistics the mass error, and the behavior is first order for all the cases. And this is the comparison of the shape between the numerical method and analytical method. So we could see a good agreement. For the phase change test cases, the first one we will have the Stéphane problem, which is we used is a first 1D problem. You have paper in the left, liquid in the right, and you have a constant temperature mountain condition at the left. The temperature distribution is like this, and the horizontal one is the saturation temperature. So for this problem, there is an analytical solution, and then we compare our result with analytical solution in the left, and the final result is first order. For the sucking problem, actually it is almost the same structure as the previous one, but the initial temperature is different. Now the temperature inside of the vapor is saturation temperature, and temperature at the liquid is higher than saturation temperature. And for this problem also we have an analytical solution, which is this dot point for the position of this interface, and the line is our numerical result, and the middle one is the temperature distribution along this x direction. So final result is also around the first order. And for a 3D problem, which is Scriven problem, we initially have a vapor bubble inside of the liquid, and because of the temperature is higher than saturation temperature in the liquid side, then the bubble will expand, And for this problem, we also have this Xiangbin analytical solution, and this is the compared with analytical solution of this radius, and this is temperature distribution, and this is also first order. And for the rising bubble with phase change, I only give the behavior of this bubble, which is initially we have a bubble in the left, and because of the temperature of the liquid is higher than saturation temperature, this bubble will expand, and because of gravity, this bubble will rising. And so in this figure, the different colors of the shape represent the shape of the bubble at different times. And the top one with surface tension higher than lower than the bottom one. So you see that the bottom one seems more like a spherical one. And then follows the temperature field. And for the film volume, I also only give the phenomenon, which initially you have left a vapor bubble, and then you because of phase changes, the bubble will rising, and finally there will serious bubbles, and these bubbles will merge. So finally we come to the nucleate boiling simulation. First we want to compare our result, numerical result with the most successful boiling problem experiment in Buch's experiment. And the left figure shows the experiment setup, that you have a brown solid bottom, and on top of this solid there is a gray titanium, which is the heat plate with a thickness of 500 nanometers, and because it provides the heat to the liquid region, then the liquid will transfer to gas. And we choose a case which is with superheat around 13 degrees, and in this case the heat flux provided by this heating plate is around 125, which is a constant. And the property of the property of the water, the liquid is water and water vapor, which is at the standard case, condition. And for our numerical setup, which is shown in the left, which is almost the same as the previous experiment setup. And for the initial condition, for the initial temperature distribution, actually, Buch get this initial temperature distribution, and to numerical match the temperature, the previous temperature heat flux distribution is not good, because if we're using this one, then the temperature is not the temperature gathered in the experiment. And then L'ubomír proposed a method with the heat flux distribution, which is almost like a linear distribution, and by this heat flux distribution we get this initial temperature field. And for the initial radius of the bubble is 10 microns, also proposed by L'ubomír, and this radius is small enough to consider in the initial region. And then we compare the height of the bubble and maximum radius of the bubble between the experiment and the numerical. In the left we have the height of the bubble, in the right we have the maximum radius of the bubble, and the circle hollow point is the experiment. Others are the results with different spatial resolution, and then we can see convergence to the experiment. And because of time limit, if we're using higher meshes, high level meshes, then we can get a better result. And for the comparison between the bubble shape, between the numerical result and the experiment in the early stage, the agreement is relatively well, but in the later stage, you see the red line and the thick red line. There's like some difference. And there are a lot of reasons. One possible reason is that the initial temperature region in the liquid side is not we think of, not we get through the temperature equation. And then we compare the heat flux, average heat flux, and the temperature distribution at the solid surface. So here, these two figures are temperature at the two different times. So we just need to focus on one time. And in this time, we see that the temperature along the solid surface of the experiment is agree with this numerical result, except the cases with the roughest meshes. And for the heat flux, for the right figure, we can also observe similar behavior, that the higher level cases is behave better than the roughest cases. And then we come to micro layer. So micro layer can be divided into several regions. Here we have the contact line region, and here we have the duetting region, and here we have a neck. And this is almost a flat plate. Plate is a micro region, main micro region. And then we have a transition region connecting the outer of the micro layer and the outer of the boiling bubble. And the first one we discussed is the micro length. In our simulation, the micro length is defined as the depends at the position of the this is theta. This theta minus the position of the contact line. And for our simulation, it's proportional to one third power of time minus a linear term, which is like this one. So this is a fitting result of the maximum level of mesh. And in the right and the left, we have the result for different meshes. And then we come to the thermodynamics and energy. Here, the left is the temperature distribution at different times, and the right is the heat flux at different times. And the conclusion is that in the micro region, temperature increases from the inside to outside, and while the heat flux from the solid to liquid remains relatively high. And for the mass flux along the bubble interface, I have this flux at two different times. Let's focusing on one type, which is the right one. So you see the colors represent the level of the mass flux, and you see that at the micro region, the mass flux remains high level, and the maximum mass flux happens at the stable point and also at the transition region, which is consistent to the result that get by L'ubomír. So and then I give the temperature feature of one point at the solid that the position is x equals to 0.15 millimeter, and this is the temperature versus time of that point, and the different colors represent that the point is covered by different region. for the blue one, that original the point is out of the is not covered by the boiling bubble, and then as the boiling bubble expand, this point will expand by the micro layer, the red region, and finally, as the triple point, the contact line pass through this point, then it will end into the bubble filter. And this is temperature change, and this is heat fast change, and you could observe a dramatically change inside of this at the boundary of this of the micro layer. And finally, we then come to the mass transfer contribution of the micro layer to the whole boiling bubble. Here I give the ratio of the mass transfer rate to the whole boiling bubble, and at a different resolution, space resolution, and I get an average around 45. And in the right, I just do a statistical work, which is I have y-axis is the ratio of the mass transfer contribution to the whole boiling bubble, and axis the ratio of the surface of the micro layer to the whole boiling bubble, and we found that it's 45, and this number is between the experiment result, which is given by Butch in his papers, is that this is around 30% to 50%. And when it comes to the micro layer thickness, at first I was using a method, a law proposed by Tessio, and the micro layer thickness is like a behavior like this, which is based on Landau-Lavage film theory, and later I found that this equation is not valid because there is no limit. So let me explain. So this gamma RB actually represents the radius of the transition region, and in this model there is no limit because RB is increasing, so gamma RB is increasing, and but in the Landau-Lavage film theory, there is a basic assumption that the radius of the local region. I just want to. The radius of this local region should be limited by some length scale, because this radius is big. If bigger than some length scale, then the outer region will be not affected. This region, and Mandip, Sunny, and I proposed a limit which is the viscous length, which is LV, and the capillary length, which is L sigma, and the radius of the local transition region shouldn't be bigger than this L sigma and LV. And so based on this limit, and also method 32, which is the Landau-Lavage film theory, we have the figure on the right, and in the left I get the numerical result of the thickness changing with time, and in our simulation we have a really oscillative result because of the it is a little bit difficult to identify the outer region of the micro layer, but the minimum one is around 1.5, 1.68 for the red line, and for different spatial resolution we get a good convergence, and for the right one is based on the Mandip and implement this model, then we have a lower prediction. But the total the difference is relatively small. And then comes to the contango impact, and this figure is the change of the maximum radius along with versus with time, and the circle is the experiment point. So when you're increasing the contango, you actually the growth rate of the maximum radius decrease. The reason is between these figures. Let's focusing on this left bottom figure, which is the position change, the position of contact line changing with time, and you see that when you're increasing the contact angle, the motion of the contact line decrease. And this is the reason that the microlayer length in the bottom right decrease. And because of the length of the microlayer decrease and the contribution of the mass flux and the energy to the whole bubble decrease, which then lead to the slower growth of the bubble. And the above reasoning can be explained by duetting theory. And I here just give another description, which is initially you have an interface with, here in the left is 30-degree interface, and in the right is 60-degree interface, and then you have phase change suppose the time is delta t, and then we this point will move to a unit length, and both for the right case, because we suppose that the superheat is the same, and in these two construction, you will find that this movement create a smaller curvature than the right one. So the surface tension, the height function, the curvature calculated at this position is smaller than the J-firm surface tension calculated at this point is smaller. And finally you get this relationship, which is as you're increasing the contact angle, the relative curvature created by this move will be stronger, which means that the microlayer contact line move faster and the microlayer decrease faster. And then we come to the effect of individual heat transfer resistance. So actually, the individual heat transfer resistance can be expressed by the equation in the figure, which is first you have this, you have the equivalence of the heat flux by resistance, and this gamma is the heat transfer resistance, which can be tuned by accommodation coefficient of omega. So typically, if you increasing this omega, then you will get a lower heat transfer interface heat transfer resistance, and then the heat flux from the solid to the liquid will be increased. And by this logical, that means if we increase the omega accommodation coefficient, then the bubble growth will increase. But in our simulation, this is not totally the chance. So in our simulation is that so at first you increase the accommodation coefficient from 0.003 to 0.5, and the bubble growth rate will increase. But after that, it reach a plateau, and then when you're increasing omega, the growth rate decrease. So what's the reason? Actually, it is because of the rupture of the microlayer. So here the macro change at different omega. I will take one for example. So in this right figure, we actually have this macro layer at first continuous, and then at time 0.35. Okay. I have also 10 minutes. So you have two types of rupture. First is the rupture at the beginning of the macro layer, which is almost at the neck. And the second type is that the rupture is at the tail of the macro layer here. And for the impact of this, the later rupture is more significant because if you rupture at the tail, then you have the long macro layer has two ends of the triple point, and then because of the receding of the macro layer, it will shrink to a bump, and this significantly shrink the length of macro layer, and then it will affect the heat flux contribution to the whole bubble. Then the growth rate will decrease. And from this figure, we find that the later rupture prefers to happens in the cases one with higher accommodation coefficient. And then we later to try to investigate the relationship between overall bubble, boiling bubble, and the macro layer behavior. So here I investigate Laplace number impact by tuning the surface tension and keep everything else constant. So in the left is the surface tension with a lower surface tension, which means lower Laplace number, and in the right we have higher surface tension. And in the higher surface tension case, we have a more stable and spherical bubble. And if we in fact state in the small angle with smaller than 90 degrees, then that means that the ratio between the height of the bubble and the maximum of the bubble will be higher. That means if we have the volume the same in the left and in the right, the basement of the right will be smaller than the left, and then you will typically get a short length of the macro in the right cases. And so here just in the left I give the ratio of the height and the maximum width of the boiling bubble, and in the right I give the radius versus with time at a different Laplace number, and we see that the maximum appears to be the smallest surface tension, because at this case the basement will be bigger. But another interesting observation is that still on Laplace number, but this time we are tuning viscosity, the channel will be different. So here I give two examples. One is the viscosity, which is 0.1. Another is 100 times of the previous one. And in the previous Laplace tuning experience, we found that if we increasing the Laplace number by tuning the surface tension, then the growth rate of the bubble will decrease. But in this case, if we increasing the Laplace number by tuning this viscosity, the trend is opposite. The reason is that also the macro layer length will be bigger when the Laplace number is small in the right case, but the thickness of the macro layer will be bigger, much bigger than the left, and because of this bigger thickness, the heat flux inside of this microlayer significantly decrease, and that's the reason that decrease the heat flux transfer from the solid to liquid. And then we get this relation when you decreasing the Laplace number, you have a decreasing trend of the growth rate of the maximum bubble radius. And this is the instantaneous heat flux along the solid surface, and the green one is with higher Laplace number. You see the length of the microlayer is bigger, which is the experience from the first case. But the thickness, because the thickness is smaller than the heat flux will be different. And this is the thickness and the length of the microlayer. So finally, we come to the boiling on rough surface, which is this one. A boiling started from a small radius and it will expand, and the structure here is some grooves with rectangle shape. And for this, I think the most interesting is that the behavior of the heat flux and temperature. For temperature, I illustrate the temperature distribution using colors, and from the top to the bottom is the direction of time increasing, and you will find that some green colors, some dark colors appears, and this means the temperature at this region is lower, and this region is corresponding to the region that is covered by the microlayer. So we see that microlayer is contributed to the decreasing of the temperature. And then when we observe the heat flux, also from top to bottom is the time increasing direction, and we found some light color, which means the high heat flux, typically at the top of the surface. But interesting that we also find some region with high heat flux at the left corner of the grooves. And then I investigate that this is because of the we think that the temperature near the interface is lower, and then the temperature lower temperature is bring to the bottom because of this vortex motion. And I think this motion is important, but I think that the lowest temperature will not be only at this point if we have different shape of these grooves, because of the vortex structure will be different. But this needed to be more calculation in the future work. So overview. So I will give a conclusion that what I have done is in the previous 3 years is that I developed a phase change model and in Basilisk, and I solved, which means I solved the surface tension equation, temperature equation, and added some models to improve the behavior on the embedded solid cases. And then I validated this code, and then we investigate the boiling phenomenon based on this code, mainly on the contact angle impact and heat and the surface tension viscous analysis using Laplace number, and all those the heat transfer resistance, interface heat transfer resistance impact. And also we have a brief exploration of nucleate boiling on rough surface. And for future work, I think one aspect is that we can enhance The second direction, second series direction in that we could explore the 3D simulation of nucleate boiling. And then study the effect of surface roughness, particularly when roughness is comparable to microlayer thickness. Then we are interested to investigate also interested in other regions' impact on contact line movement, because although the energy contribution of the contact line is small, according to Urbano, but its impact on the contact line motion can shorten or extend the microlayer, so it's also interesting. And finally, it's also interesting to explore the influence of the Jacob number and the initial temperature distribution on nucleate boiling, because currently whole of our work is based on the Jacob number around 30. So it's needed and also interesting to extend this Jacob number to higher regions or lower regions, and interesting phenomena will also be found. And also that's what I've done in my previous work, and thank you for your attention, and also sorry for all the accidents that happened in the defense.